Hello everyone, welcome to today's session. We're going to explore transport layer issues in data center networks, or DCNs. Now, you might wonder, what exactly is a DCN? Think of it as the giant backbone of modern internet services like Google Search, Amazon Web Services, or Facebook. Millions of servers inside data centers communicate through networks, and TCP, Transmission Control Protocol, is the most common transport protocol they use. But here's the catch. TCP, though reliable, struggles in DCNs, and that's what we'll unpack today. TCP and DCNs. TCP has been the internet's workhorse for decades. It manages congestion, retransmissions, and ensures reliable delivery. However, in a data center environment, the traffic is very different. Some flows are tiny, like a short chat message. These are called mice flows. Some are medium, like a quick file transfer, called cat flows. And some are massive. Think of moving huge video datasets, called elephant flows. Now imagine all these different animals trying to squeeze through the same narrow doorway. The result? Congestion and inefficiency. TCP Incast. Let's start with the TCP Incast problem. Picture this. You're at a birthday party. You ask 20 friends at once to shout happy birthday back to you. What happens? You get overwhelmed, and you can't hear clearly because everyone shouts at the same time. That's exactly TCP Incast in a data center. An aggregator server requests data from multiple worker servers. All workers reply at once, and the network buffers, like the party host's ears, get overwhelmed. Packets are dropped, leading to timeouts and slow responses. This is a big issue in web search, MapReduce, or distributed storage systems. How to fix it? Researchers suggest redesigning TCP, or even replacing it with smarter protocols that handle bursts better. TCP Outcast. Next is TCP Outcast. Imagine two queues at a supermarket checkout. One queue has many shoppers with big carts. Another queue has just a few shoppers with small items. But the cashier serves the big cart line continuously, and the small cart people keep getting ignored. Frustrating, right? That's TCP Outcast. In DCNs, when a large group of flows and a small group of flows compete for the same switch port, the small group loses out badly. This happens because most data center switches use drop-tail queues, which unfairly drop packets from one side, a problem called port blackout. Solution? Use smarter queuing techniques like random early detection, RED, or stochastic fair queuing, SFQ, which share the bandwidth more fairly. Queue buildup. Now, let's talk about queue buildup. Think of a highway. Small cars, mice flows, and giant trucks, elephant flows, share the road. Trucks move slowly but take up lots of space, while small cars want to zip by. In DCNs, elephant flows hog the network buffers. Mice flows either get delayed or dropped entirely. The result? Latency increases and applications slow down. Fix? Instead of reacting only when congestion happens, networks need a proactive congestion control, reducing sending rates before queues become full. Buffer pressure. Closely related is buffer pressure. Imagine a school canteen. One big group of students sits at every table, leaving no space. Suddenly, a burst of younger kids arrive, but there's no room left. They're pushed out. That's what happens when elephant traffic continuously fills up switch buffers. When mice flows arrive in a burst, they have nowhere to go and get dropped. Again, the solution is the same. Keep buffers lightly occupied, instead of always full. Pseudocongestion effect. Now comes something unique. Pseudocongestion, which happens in virtualized data centers like Amazon EC2. Here's a real-world analogy. Think of a busy office where employees share just one printer. Even if the printer is free, you can't print until the manager schedules your turn. If scheduling is slow, it feels like the printer is always busy, even if it's not. In DCNs, multiple virtual machines, VMs, share the same physical server. The hypervisor, like that manager, schedules access. If scheduling is delayed, VMs think the network is congested, even when it's not. That's why we call it pseudocongestion. This leads to unstable throughput and high delays. Solutions? Either improve the hypervisor scheduler to reduce delays, or modify TCP so it can tell the difference between real congestion and fake congestion. Final summary. So, let's recap. TCP Incast too many replies at once, buffers overflow. TCP Outcast small flows unfairly lose to large flows. Queue buildup elephant flows hog space, mice flows suffer. Buffer pressure bursts of mice traffic get dropped due to greedy elephants. Pseudocongestion delays from virtualization trick TCP into thinking the network is congested. All these show that traditional TCP isn't well suited for data centers, and researchers are working on better congestion control and scheduling techniques. We've seen how DCNs face unique challenges at the transport layer, and why simply relying on old TCP isn't enough. Next time you do a Google search or stream Netflix, remember, behind the scenes, thousands of tiny mice and giant elephants are trying to share the same network roads. Thanks for listening, and keep learning.